Okay, now we're going to go a little further into water. Before we do that, I need to explain how the electrons are configured in these outermost shells and in the shells that are used for combining. Realize that electrons are extraordinarily small particles. Compared to a proton, they're 1,000 times smaller. And they move very, very quickly while a proton just kind of vibrates back and forth. An electron moves so quickly that particles accelerated that fast have what we call wave characteristics. Think sound waves. That they move so quickly that they're actually a wave as well as a particle simultaneously. Now that's a little more atomic physics than I want to get into right now, but it gives you an idea of the speed involved here. Thus, the quickness of interaction when these atoms are put of column 1 and column 7 are put in proximity of one another. Sometimes it takes an interjection of an outside heat source, such as a flame, to produce the desired reaction, but it's quite a reaction. Now, if we're talking about helium, it has one electron spinning one way and one electron spinning the other way. It's a full shell, and it is said to have a full 1s shell. Now, if you have 3 electrons, you're going to have the full 1s shell and one other electron added to the 2s shell. The next electron will spin the opposite way. Then you go to the next electron, it goes into the 2px. The next one is 2py and 2pz. Notice they don't fill up as they go across. They're one electron in each shell first. Then they come back, spinning opposite, of course. Now, notice I purposely made the spin different for 1s and 2s because it really doesn't matter which way you point out that the spin is, as long as you indicate that it's opposite. Okay. Now let's talk about water. Now, one of the things about chemistry that students understand readily is if you have 4 atoms over here and this little arrow indicates goes to form or is an arrow indicating a reaction, must have 4 atoms on the other side also. So if you look at this in perspective, you've got oxygen with 2 atoms here, 2 hydrogens there. On the reaction side, the completion side, if you wish, you have 2 hydrogen atoms and 1 oxygen atom. It cannot exist. It must always, in a balanced reaction, you have the same number of atoms on either side. So, in order to make this work, we take a factor which is very important. The factor being that you can use multiples of these diatomic molecules or any molecule by putting a number in front. Well, if you put 2 in front of the hydrogen, you have 4 hydrogens here and 2 oxygens. And if you put a 2 in front of the water, you have 2 hydrogens times 2 or 4 hydrogens, and it multiplies everything in the molecule, so it's 2 oxygens also. We say this is a balanced chemical reaction. Now, many of you will wonder why in the heck that I am starting everything based on water. Well, water is a really, really unusual substance. And why is it unusual? Because water has oxygen and it's 6 electrons. combine with hydrogen to form water. Notice the way I've written it. I've got the electrons reasonably well distributed around, but if you'll note, there is a center of negativity at the bottom of the water molecule. Electrons don't play well with each other. We would give them the bad kid on the block. If your mom was refereeing, the kids should put them in the opposite corners because they just do not like each other. This negativity or repulsivity, as it's called, has the electrons getting as far away from one another as they can, period. Now, what we have here with water is we have a negative side of the molecule and a positive side, with the hydrogen on top as the positive side and the bottom the negative side. This is very important. This is called polarity. Now, polarity is easy to understand. Poles, yeah, positive and negative poles. But polarity of water is an amazing factor for your existence. For instance, to prove that water molecules have an adherency one for the other, in other words, a positive end of the next type of water molecules down below would adhere or attract to the negative side. The hydrogen would attract to the negative side of the water molecule. This polarity exists demonstrably. You can get a glass plate. You probably use any kind of plate, but glass plate's the easiest for illustration. Get a dropper and put 2 or 3 drops of water in the middle of the glass plate, and slowly take your finger and move through the water. You'll notice the water tends to be drawn along with your finger. Now, your finger doesn't have a great attraction for the water, but the water molecules have a greater attraction for one another. Now, how is this more widely demonstrable? If you go to swim in the pool or the lake, you should sink like a rock. I mean, your density is considerably greater than water, and thus you should splash in and splash down, but you don't. Now, there's a variety of reasons for that. One is the factor of water molecules' adherency for one another resists your pushing them away. This is called buoyancy. And this, again, is a practical illustration of polarity of water molecules. Thus, you're able to float on water. Now, how does that practically apply? Get yourself a paper clip and open it up and get it perfectly level. Get yourself a bowl of water, or if you're going to get a glass of water, it's not going to work as well. If you get a glass with a big mouth, it might. And get yourself a pair of tweezers and set that paper clip barely touching and release it. If you do it right, it'll actually float. Now, what the heck is that about? You got something that's really dense in relation to the water molecule, and it's not sinking like a stone, just as you did not sink like a stone. Very important factor. This surface tension, as it's called, is the reason that boats can float and don't sink to the bottom, that you can float and don't sink to the bottom. The resistance of the water molecule from being pushed apart from other molecules. Now, this adherency has illustrations which will blow your mind. Many of you have heard of the giant sequoia and seen pictures of them in books, and quite a few have probably actually visited them. Now, the sequoia have very shallow roots, so I think 15 feet is the depth of the deepest root. But they go up 200 feet or so, many of them 100 feet or better. Now, the question that's got to come to your mind is, how does the water get from the bottom of the 15th foot of the root, which is absorbing moisture from the soil, and get to the top of the 200-foot tree, to the leaf? Now, everyone in the place understands that there aren't trained squirrels on the side of each tree and running around in their little squirrel cage pumping water up to the top of the tree. Something has to provide it. And it's found in nature that at the top of the tree, when one molecule of water evaporates from the top leaf, another molecule is drawn up. So this polarity of the surface tension, this unusual factor caused by the polarity of water, enables water to bring molecule by molecule drawn up from the base of the plant down into the root system all the way to the top, molecule by molecule. Wow. One of the strongest forces in nature. As a matter, it's almost an anti-gravity force because it is capable of resisting gravity by drawing it up. Now that is explainable energy-wise a bit differently, but for our purposes here, realize that the molecular interaction between water molecules is so strong that it can overcome a 200-foot gravitational resistance to bring water to the top leaf. And obviously it goes to the other leaves too. An amazing, amazing characteristic that water has. That's the reason I use water as the opening illustration for general chemistry, as some of you all have interacted with. And some of you may have noticed that if you take a rock and throw it into the lake, thunk, all the way to the bottom of the lake, but if you jump in, you don't go to the bottom of the lake. And you may have wondered, I wonder why I don't drop to the bottom of the lake. This is the reason. So it gives you a reason for life. Let's see if I have any more things to bore you with this morning. I think I probably have bored you as much as possible for the first lecture. I hope it helped, and I hope it gave you an understanding of all these interesting factors of water and Dmitri Mendeleev's periodic table, the interaction of atoms to form that magic number of electrons of 8 provided by the outermost electrons of the elements, and shown you a pattern, the pattern of water as it interacts and it moves, and the pattern of Dmitri Mendeleev's brilliant periodic table of the elements. Now, he did not come up with the finalized version because, he started this back in the early 1900s. We've added to it over the century. And today we have, 106, 8, 10 elements. The latter elements have been added as they have actually been created. And the way they do that is they'll take a highly dense element and bombard it with high-speed neutrons and protons, hoping that they will be captured in the nucleus, thus changing the mass of the nucleus, thus changing the element itself when the protons are in. These elements are mostly unstable. Some of them have what's called a half-life. In other words, the length of time they exist. in seconds, thus are not important in general chemistry. But the column 1 through 8 should be looked through. Now, reference points. There are a myriad of authors, general chemistry, which you could use as a reference as you go through this course. But I like Zumdahl. Now, Steve Zumdahl's been around a long time, and he's written textbooks for high school and college general chemistry. I don't think he receives near the credit he receives for the complete approach that he does. Now, I approach things differently because I try to provide as much detailed and understandable explanations as possible. But Stephen is complete, and I think you'll enjoy. And unlike the $250, $300 textbooks that they try to sell you at the college bookstore, you can go out and find one of these used Zumdahls, some of them 20 years old or better, for $5, $6. And they will provide you plenty of reference for this course. And I recommend that you don't waste your money. Your girlfriend or your boyfriend will want you to help them out on Saturday night for the costs of the movie.